Somewhere out in the dark on a photograph taken by a patient telescope, a single faint smudge of light hangs against the black. All around that smudge, reaching outward in every direction farther than the mind can follow, there appears to be nothing at all. The smudge is a galaxy, a slow wheel of hundreds of billions of stars. The nothing surrounding the galaxy is, by every instrument we've ever aimed at the sky, almost exactly as empty as the eye reports. Almost nothing. And yet, that almost nothing, so softly that no one would ever catch the motion, is doing something quietly astonishing. The emptiness is holding the entire universe in its shape. Tonight we're going to drift, without hurry, through the spaces that lie between the galaxies, the vacant places that turn out not to be vacant, the threads that no telescope can quite bring into focus, the framework that assembled everything ever assembled. Our subject tonight is the space between the galaxies, the geometry almost no one ever mentions, precisely because so little seems to occupy it, and the surprising truth that the dark gaps between the bright things are themselves the grandest, the strangest, and very quietly the most beautiful structure that has ever existed. We will begin somewhere close to home, just past the front step, and then move outward together, one slow layer at a time into the deeper country of the cosmos. Before we take a single step, let me hand you the one strange gift that makes this whole journey possible, because the gift will change how you see everything that follows. When you look out into space, you're also looking backward through time. Light is swift beyond ordinary comprehension, crossing the distance from the moon to your eye in a little over a second. Yet the cosmos is so wide that even light, the fastest thing there is, arrives late. The sunlight warming your window left the sun about 8 minutes ago. The light of the nearest bright stars set out years before tonight, and the faint smudges of the distant galaxies carry light that began its crossing before the earth had formed, before the sun had gathered, in some cases before anything you would recognize as a star had ever shone. So every deeper layer we visit tonight is also an older one. To travel outward through this architecture is to travel down into the past. The farther we drift, the younger the universe we are seeing, until at the very edge of sight we reach light almost as old as time. Keep that quietly in mind. We're not only mapping a place, we're drifting down through the memory of everything. Now bring the night sky to mind. Even if your own window looks out on nothing but streetlight, picture the version of the sky that lives in your memory, built from photographs and clear nights half remembered. The stars seem near. They fall into patterns draped across the black like old lace. Some look close and some look distant, yet all of them appear to belong to a single ceiling, hung at one height, the way the ceiling of a room reads as one flat surface, even though every point on that surface sits at a slightly different distance from your eyes. The sky looks like a ceiling. That is the first illusion we need to set down tonight, and the illusion is a very old one. The stars your eyes can gather on a dark night are not fixed to any ceiling. Those stars are scattered through a volume so enormous that the word enormous cannot begin to carry the weight. The nearest star to our Sun, a small dim red companion named Proxima Centauri, sits about 4 light-years away. 4 light-years is the distance light needs 4 whole years to cross, moving at the one speed nothing is permitted to exceed. Send a friendly hello in that direction tonight at the speed of light, and the greeting would arrive in time to meet whoever happens to be reading in the year 2030. and Proxima is our closest neighbour of all. Nearly every other star you can see is far more distant. Some of the bright ones stand hundreds or thousands of light years off. That soft pale band arching across a truly dark sky, the band we name the Milky Way, is our own galactic disk seen edge on, a flattened city of perhaps 400 billion stars stretched across 100,000 light years. We live inside that city. We are not gazing up at the galaxy from outside. We are peering through one thin slice of the disk from a spot about 2/3 of the way to the rim, tucked in a small spur of stars between two of the larger spiral arms. The night sky is not a ceiling. The night sky is the inside of a galaxy. Try for a moment to feel the true depth of the thing you are lying beneath. When your eye lands on one bright star and then flicks to another that appears to sit just beside the first, those 2 points of light may in truth be separated by a gulf so wide that light itself needs 1,000 years to travel from one to the other. They only appear to be neighbours because they happen to fall along nearly the same line of sight, the way a nearby candle and a distant street lamp can seem to touch when you close one eye. The constellations are not real groupings. The constellations are chance alignments of stars at wildly different depths, sketched onto a flat imaginary dome by minds that could not yet see the third dimension of the sky. Once you know this, the night loosens and deepens. The dome dissolves, and what remains is a vast open room with no far wall, a room you are standing inside rather than looking up at. Now rise gently, the way a balloon lifts, until the galaxy falls away beneath you and the whole shape resolves from above. What a lovely object the Milky Way turns out to be. A soft, luminous wheel of pale starlight, turning slowly, warm and yellow at the centre, wrapped in a hazy spherical halo of older and dimmer suns. The galaxy looks complete, self-contained, the sort of thing that, all on its own, could seem like the entire point of creation. And around the bright wheel, unseen, lies something far larger than the light, a great rounded cloud of dark matter, the invisible material that outweighs all the stars several times over, holding the spinning disk together against speeds that would otherwise fling the outer stars away into the night. We cannot see that halo. We can only feel the grip of the halo in the motion of the stars. Keep the dark halo in mind, because the same invisible substance, on far grander scales, turns out to be the true scaffolding of everything we will meet tonight. The Milky Way is not the entire point. Float a little higher, and other galaxies begin to appear. The first one you notice, just over your left shoulder, is a slightly larger spiral, close in shape to your own. That neighbour is the only galaxy most of us know by name, and out of respect for the time we have spent with Andromeda on other evenings, we will walk quietly past that spiral tonight without letting the story settle there. Others wait nearby, a small, ragged, irregular galaxy here, a tidy little dwarf elliptical there, a scattering of faint scraps of light that are themselves entire galaxies, only very small ones. Roughly 80 in total, all of them drifting inside a soft, invisible pool of dark matter that gravity has gathered around the whole gathering. This family has a name. We call the family the local group, and until you truly stop and look, the local group is easy to mistake for the whole universe. The mistake does not last. The local group is one quiet household in a far larger town. The town carries the name local sheet. Here is one of those terms astronomy hands out to things that sound modest and are anything but. The local sheet is a flat, extended stretch of space, about 34 million light years from side to side, and only about 1.5 million light-years thick, holding the local group along with a dozen or so other smallish gatherings of galaxies. The shape, as the name promises, is a sheet. A soft, slowly turning page of galaxies whose motions all lean gently in agreement, all of them travelling through the wider cosmos in roughly one direction at roughly one speed. Picture yourself inside a great drifting crowd, everyone spaced far apart, everyone walking the same loose way without quite knowing the reason. That crowd is us. That crowd is the immediate neighbourhood, and here is the strange, lovely detail about the local sheet. We do not sit at the centre, we sit on an edge, and just past that edge lies a great hollow region of very nearly nothing. The hollow is called the local void, and the local void sits directly beside us. This is not the famous emptiness you may have met in other space videos. That other void lies much farther off, and we will travel to that one later tonight. This one is close. So close, in fact, that the local sheet is being very gently shoved along by the local void. An astronomer named Brent Tully first noticed this hollow in the late 1980s, and Tully has since given most of a long career to charting our cosmic surroundings, with a patience that is hard to believe. He and his colleagues showed, using the motions of more than 18,000 galaxies, that the local void is vast, though no one can say quite how vast, because part of the hollow hides behind the crowded centre of our own galaxy, where our view is blocked. What the team could measure was the effect, the local sheet, and every one of us riding along with the sheet is sliding away from the local void at about 260 kilometers every second. Not because the hollow is doing anything dramatic, but because everything surrounding the hollow is denser, and the denser places pull ever so slowly on us. We're being coaxed out of the empty room and into the busier ones. Our whole neighbourhood rides a slow, gentle current, leaving a vacant house behind. There is something quietly lovely in that image, in a way I did not see coming. Right now, in this very moment, the small blue planet you're resting on is drifting along a gravitational tide. You cannot feel the drift. Nothing in an ordinary day so much as hints at the motion. Yet the drift is real. The Earth rides the sun rides the galaxy rides the local group rides the local sheet, and the local sheet slides sideways through space at 260 kilometers a second, away from a hollow no eye can see. And the sliding has been going on for billions of years, without haste, without strain. The way water moves down a channel that water never chose. Now here is where the story of our motion takes a turn that genuinely surprised the astronomers who uncovered it, because for a long time we understood only half of the reason we move. We had assumed, quite naturally, that a galaxy drifts because something massive is pulling on that galaxy. Gravity attracts, dense regions tug. So astronomers went looking for the great mass hauling our whole neighbourhood along, and they found some of the pull they expected in the crowded clusters lying ahead of us. But the sums never quite balanced. The known concentrations of galaxies out in front simply were not heavy enough to explain how fast we were actually going. Half of our motion had no source anyone could point to. The answer, when a team led by the astronomer Yehuda Hoffman published the finding in the year 2017, was as elegant as it was strange. We're not only being pulled from the front, we're also being pushed from behind. Behind us, in the direction opposite to all those distant clusters, lies an immense region where galaxies are scarce, a supervoid so empty that astronomers named the region the Dipole Repeller. Now, a void cannot literally push, emptiness exerts no force. But picture a ball resting on a level floor. If a heavy weight sits on one side of that ball, the ball rolls toward the weight. And if the other side of the room is simply bare, then relative to the crowded side, the bare side behaves exactly as though the emptiness were shoving the ball away. Everywhere around the void, matter is being drawn off toward the denser regions, thinning the void further and leaving our neighborhood leaning away from the hollow and toward the crowd. In the language of the discovery, an underdensity pushes as surely as an overdensity pulls, and the remarkable thing Hoffman and his colleagues showed is that the push and the pull are of very nearly equal strength. Two great influences, one attracting from ahead and one repelling from behind, together set the pace of our long fall through space. There is a number attached to that fall, and the number is oddly moving once you know what the number measures. Our whole local group is moving, relative to the ancient background glow left over from the birth of the universe, at about 630 kilometers every second. For decades that speed was a small embarrassment, because the visible attractors ahead of us could account for only about half of the figure. The discovery of the dipole repeller closed the gap. The empty region behind us supplies the missing half. So when you rest tonight, feel this if you can. You're being carried through the cosmos at more than 600 kilometers a second, drawn forward by distant crowds of galaxies, and eased forward from behind by one of the emptiest regions in the known universe, and the two forces are so finely matched that neither one alone could move you. You travel on the balance between a crowd and a void. How does anyone measure a current like this? A flow of galaxies across hundreds of millions of light years, when we are riding inside the current ourselves and cannot step outside to watch? The answer is a slow and beautiful piece of work called cosmic flows, built over decades by Brent Tully, by Helene Courtois, by Daniel Pomereed, and by their colleagues. The idea is this: every galaxy is carried outward by the general expansion of the universe, and that part of the motion is predictable. But laid on top of the smooth expansion is a second, smaller motion, the personal drift each galaxy has because of the gravity of everything around the galaxy. Astronomers call that extra drift the peculiar velocity, and the peculiar velocity is the fingerprint of hidden mass. Measure the true distance to a galaxy by one method, measure the galaxy's speed by another, subtract the smooth expansion, and what remains is the private motion, the little lean toward whatever is pulling and away from whatever is empty. Gather tens of thousands of those private motions, draw them as arrows across a three-dimensional map, and the arrows begin to reveal the streams. Watersheds appear. Rivers of galaxies pour toward the dense places and away from the hollow ones. The invisible landscape of gravity is drawn at last by the motions of the things riding across the landscape. There is one measurement underlying all of this that deserves its own quiet mention, because the measurement is how we know we are moving at all. Cast your mind back to that faint background glow left over from the birth of the universe, the oldest light there is, reaching us from every direction. In principle, that glow should be almost perfectly even across the whole sky, the same temperature wherever you point. When astronomers measured the glow properly, they found the light very slightly warmer in one direction and very slightly cooler in the opposite direction, a smooth gradient across the entire sky. The explanation is beautifully simple: we are moving. When you travel toward a source of light, the light is very slightly compressed and appears a touch warmer and bluer. travel away, and the light is stretched and appears a touch cooler and redder. Our whole galaxy is sailing through the universe, and the ancient light records the sailing, warm on the bow and cool on the stern. Astronomers call the pattern the dipole, and by measuring how large the temperature difference is, we can read our own speed straight out of the oldest light in existence. That is where the figure of about 630 kilometers a second comes from, and that is the number the flow maps and the dipole repeller and the great attractors all had to explain. Think of what that means. We cannot step outside the universe to watch ourselves move. So instead we measure our motion against the faint warmth of the beginning of time, using a glow that's set out before there were stars, and the glow tells us patiently and precisely exactly how fast we are travelling and in which direction. The universe left us a speedometer 13 billion years before anyone existed to read it. One of the loveliest and most humbling things those flow maps revealed lies almost directly beneath our feet, in the southern sky, in a direction so obscured by our own galaxy that no one had ever noticed the structure before. In the year 2020, the Cosmic Flows team announced an enormous wall of galaxies, one of the largest single structures ever charted in the nearby universe, sweeping across roughly 1.5 billion light years and partly hidden behind the dust of the Milky Way. They named the structure the South Pole Wall, because so much of the structure hangs below us, toward the southern celestial pole. Think about what that means for a moment. A structure of that size, one of the great walls of the local cosmos, sat undiscovered until only a few years ago, not because the wall was faint or far, but simply because the wall lay behind the bright screen of our own galaxy, in the one direction we find hardest to see through. The cosmos, even close to home, is still handing us landmarks we'd entirely missed. Ride the current outward a while longer, past the edge of these hidden walls, and you reach the next great landmark of our region. The landmark is the Virgo cluster, and the Virgo cluster is, more or less, the nearest large gathering of galaxies to our own. About 65 million light-years off, in the direction of the constellation Virgo, more than 1,000 galaxies hang together in a loose, gravitationally bound company. Among them stand some real giants, grand elliptical galaxies far older than the Milky Way, smooth footballs of ancient reddish stars that finished making anything new a very long time ago. The Virgo cluster is dense by the standards of the cosmos, bright, busy, and our own local group drifting outward from the local void is at the same time drifting inward toward Virgo. Never fast enough to feel, never once fast enough to feel, but slowly and faithfully the way every gravity-bound thing eventually travels. At the very heart of the Virgo cluster sits a galaxy worth pausing on, because that one galaxy gave us a photograph that changed how ordinary people picture the universe. The galaxy is called M87, a vast elliptical far larger than the Milky Way, and at the centre of M87 lurks one of the most massive black holes ever weighed, a monster of roughly 6.5 billion times the mass of our Sun. For most of a century, a black hole was a thing you could only draw, a place defined entirely by what light could not escape, which meant a thing that by its very nature could never be seen. Then, in the year 2019, a team running a planet-spanning network of radio dishes called the Event Horizon Telescope did what had seemed impossible. By linking observatories scattered across the Earth into a single instrument as wide as the planet, they gathered enough fine detail to image the shadow of the black hole in M87 against the glow of hot gas swirling around the drain. the picture that emerged, a dark circle ringed by a lopsided halo of orange light, was the first image of a black hole that human beings ever made. And the black hole chosen for that first portrait sits right here, in the bright heart of the nearest great cluster to our own, anchoring the crowd of galaxies that our whole supercluster is slowly falling toward. So now, in your mind, our address has grown longer. You live on a small blue world circling an ordinary yellow star out on the inner edge of a spur of the Milky Way galaxy, which is one of about 80 members of the local group, which is one of about a dozen groups within the local sheet, which lies on the very rim of the local void, which is being gently drawn toward the Virgo cluster. Already the sentence runs long, and we are still very near home. We are nowhere close to the end of the address, and before we travel any further outward, I want to stop and let one of those distances become real to you, because we have been throwing around light years all evening as though the words were small. They are not small. Let us take the very first step of the journey, the gap between our sun and the nearest star, and try to cross the gap honestly. The fastest object human beings have ever launched into the dark is a small spacecraft that left the Earth in the 1970s and has been running outward ever since, out past the planets, out through the edge of the sun's influence, into the space between the stars. That spacecraft travels at something like 17 kilometers every second. 17 kilometers a second is a speed no human machine had ever reached before, fast enough to cross the whole width of a country in about 4 minutes. And if that spacecraft had been aimed at Proxima Centauri, the nearest star to our own, the crossing would take somewhere in the region of 70,000 years. 70,000 years to reach the very first star on the list. Longer than all of recorded history, many times over, longer than agriculture, longer than cities, longer than writing. And Proxima is the near one, the neighbour, the first doorstep beyond our own. Now hold that number in your hand and turn to the gaps we've actually been discussing tonight. The distance to the nearest large galaxy is not 4 light years but 2.5 million. The distance to the Virgo cluster is 65 million. The distance to the Shapley concentration is 650 million. There is no engine, no fuel, no clever trick of technology that closes a gap like that in any span of time a living thing could sit through. Even if we could somehow build a ship that flew at 99% of the speed of light, an achievement so far beyond us that the fuel alone would be a problem of absurd proportions, the crossing to another large galaxy would still take millions of years as measured by anyone left waiting at home. The travellers themselves, thanks to the strange kindness of relativity, would experience far less. Time runs slower for those who move very fast, so a crew aboard such a ship might live through only a few decades of shipboard time, while millions of years poured past outside. But everyone they ever knew, and every civilization that ever launched them, and quite possibly the entire species that built the ship, would be gone by the time the ship arrived. Any crossing between galaxies is a one-way passage out of your own era, not merely out of your own address. I do not say this to make you feel small. I say this because the emptiness we have been mapping tonight has a meaning, and the meaning is this. The gaps between the galaxies are not merely large. The gaps are the reason each island of stars is, in practice, alone. Whatever is happening on some warm world circling a distant sun inside the Virgo cluster, we will never walk there, and nothing walking there will ever come here. The cosmic web connects everything gravitationally and separates everything absolutely. The threads bind the universe into a single structure while the distances along those threads make every bright knot a private country. And there is something quietly restful in that thought. Once the first sting passes, the universe is not withholding anything from us out of unkindness. The universe is simply, gorgeously, enormous, and we happen to be small creatures with short lives, standing on a warm rock, able to see almost all of it, and to visit almost none of it. Seeing turns out to be the gift we actually received, and seeing, as we are discovering tonight, is quite a lot. In the year 2014, a team of astronomers, led again by that same patient Brent Tully, did something that quietly rewrote a corner of cosmology. The team measured the motions of about 8,000 galaxies very carefully, and noticed that those motions, drawn out as flowing lines, did not scatter in random directions. The lines poured. The lines poured in great slow streams, like rainfall gathering into watersheds, toward a handful of particular places, and one such watershed, the very one we sit inside, held not only our local group, not only the Virgo cluster, but more than 100,000 large galaxies spread across an enormous region roughly 500 million light-years wide, all of them drifting gently the same way. The team had found our supercluster, the grand gathering for which the Virgo cluster serves only as the bright local hub, and they gave the supercluster a name that has stayed fixed ever since. They called our home Laniakea, which in Hawaiian means immense heaven, or immeasurable sky. The definition the team used for Laniakea is worth pausing on, because the definition is a genuinely new way of deciding where a structure begins and ends. For most of history, astronomers drew the boundary of a cluster by simply counting galaxies and marking where the crowd thinned out. Laniakea was drawn a different way by the flow. A supercluster, in this newer thinking, is the whole region across which the galaxies all drift toward a single common floor, the way a watershed on land is defined not by the shape of the hills, but by where the rain finally runs. Stand anywhere inside Laniakea, release a galaxy, and let gravity take over, and the galaxy will eventually stream inward toward the same deep gathering point. That shared destination is what makes the region one thing. We do not live at the center of that flow. We live far out toward the rim, where the water is only just beginning to gather speed, on a quiet edge, in a small group, in a thin sheet drifting slowly inward alongside the rest of our supercluster. Laniakea strikes me as a strangely comforting word. The word is not frightened of the size of the thing being named. Most of our cosmic vocabulary is small, tidy, technical. Galaxy, cluster, supercluster, neat as folders in a drawer. Laniakea is another kind of word altogether. Laniakea is a word for a place that will not fit inside any folder, and the direction our whole supercluster leans, the floor toward which all that slow rain is falling, points toward a strange dense region marked by the Norma cluster, the Centaurus cluster, and a deeper gravitational well farther out that has, for historical reasons, been called the Great Attractor. And the Great Attractor rewards a much closer look, because the region is one of the strangest and most stubbornly hidden features of our entire neighbourhood. The story of how we found the Great Attractor is one of my favourites in all of astronomy, because the story is a detective tale with the culprit hidden in the one place we cannot easily look. In the 1980s, a group of 7 astronomers, remembered ever since by the affectionate nickname the Seven Samurai, measured the motions of hundreds of galaxies across a wide swathe of sky, and found them all streaming together toward a single region, as though some enormous unseen mass were reeling the whole neighbourhood in. The pull was clear, the puller was not. Because when the astronomers looked in the direction of the flow, they found their view blocked by the worst possible obstacle, our own galaxy. There is a band across our sky, running along the crowded plain of the Milky Way, where the dust and gas and dense fields of foreground stars simply blot out the universe beyond. Astronomers call this band the zone of avoidance, and the band hides roughly a fifth of the entire sky from optical telescopes. Whole galaxies, whole clusters of galaxies, lie concealed behind that glowing curtain of our own making. And by a genuinely unlucky accident of geometry, the Great Attractor sits almost squarely behind the thickest part of that curtain. For years we could feel the pull of the thing without ever seeing the thing at all. The way through was to abandon ordinary starlight and look in the registers that pierce the dust. X-rays, infrared light, and the long radio whisper of neutral hydrogen all pass through the obscuring band far more easily than visible light, and across the 1990s and 2000s, telescopes tuned to those registers slowly lifted the curtain. Behind the zone of avoidance, they found a great rich cluster of galaxies, the Norma cluster, lying about 220 million light-years away, sitting so nearly at the bottom of the gravitational well that the cluster itself barely drifts at all, while everything around the cluster falls inward toward the cluster. Nearby they uncovered still more hidden structure, including a vast concealed sheet of galaxies now called the Vela supercluster, a giant that had been sitting behind the Milky Way, unseen the entire time. And yet, when the astronomers added up all the hidden mass they could find, even the Norma cluster and its companions were not quite heavy enough to explain the full strength of the flow. The Great Attractor turned out not to be a single object at all, but a broad, sprawling overdensity, a whole region of above-average matter reaching across hundreds of millions of light-years, with the Norma cluster near the heart. And beyond even that, farther down the same long slope, lay something heavier still. Because the real turn in the story is not the Great Attractor at all. The real turn, only very recently, is what lies behind that attractor, farther down the same long slope. In late 2024, the same patient team that charted Laniakea published fresh work. This time the astronomers held the motions of about 56,000 galaxies, a longer baseline, and sharper statistical tools, and the team reported something gentle and bewildering. There is roughly a 60% chance by their analysis that Laniakea is not the whole account, that the supercluster we had thought of as home is actually a tributary, draining slowly into something far larger, perhaps 10 times larger in volume, centered still farther out on a colossal concentration of mass called the Shapley supercluster. I want to be honest about that figure of 60%, because honesty is the whole spirit of this channel. 60% is not proof. 60% is a leaning, a more likely than not, the kind of result that tells you where the evidence is drifting without yet telling you the answer for certain. So hold this next part lightly. If the leaning is correct, then the map of home is about to grow one more line. Shapley lies about 650 million light-years away. Shapley holds some of the richest galaxy clusters anywhere in the nearby universe, packed close in a region whose gravity runs so deep that even the Great Attractor may sit partway down that same slope. And in a quietly perfect symmetry, Shapley sits almost exactly opposite the dipole repeller in our sky. remember the balance of push and pull that sets our speed. The great crowd we are falling toward, the deep floor of our basin, is Shapley. The great emptiness pressing gently at our backs is the repeller. We are threaded between the two, drawn toward the richest concentration of galaxies in our part of the universe and eased along from behind by one of the poorest. If the new analysis holds, then we're not merely drifting through Laniakea toward the great attractor. We're drifting through a far larger basin, with Shapley resting at the bottom like a vast still lake. And in the year 2025, Shapley handed astronomers something almost too fitting, a thing that ties this whole story together and points ahead to the deepest mystery of the night. Deep inside the Shapley supercluster, a team traced an enormous thread of searing hot gas, a filament running between 4 separate galaxy clusters and holding something like 10 times the mass of the entire Milky Way in gas alone. The thread was not made of stars. The thread was made of the thin million-degree material strung along the connective tissue of the cosmic web, exactly the kind of hidden matter we'll spend the second half of tonight chasing. For now, simply hold the picture. In the richest, most crowded corner of our local universe, the astronomers did not only find galaxies, they found the glowing cable of hot gas running between the galaxies, a first clear look at the wiring that the whole architecture hangs upon. The truth is that we do not yet know for certain how far the map extends, but that image of galaxies flowing like water down toward a distant floor is not one I grew into easily. And yet flowing water is exactly the way the people who study this now think about the cosmos. The universe is not a still arrangement. The universe is a slow current. Matter falls, voids drain, filaments thread, clusters gather, and the gathering and the flowing unfold across scales that human language was never shaped to hold. Hundreds of millions of light years, tens of billions of years. There is a beauty here that I would rather not spoil by pressing too hard on the description. Let us simply stay with the picture a moment longer. A great calm river of galaxies flowing in the dark. Before we pull back to the grander scales, let me answer a question you may already be holding, because the answer is one of the quiet marvels of science. How can anyone possibly know these distances or know that the whole universe is drifting apart at all? The answer, once again, is written in light. When a galaxy moves away from us, the light of the galaxy is stretched on the journey, its waves pulled slightly longer, which shifts the colour of the light a touch toward the red end of the spectrum. Astronomers call this stretching redshift, and the faster a galaxy recedes, the more the light of the galaxy is reddened. Nearly a century ago, an astronomer named Edwin Hubble, working with the measurements of others, noticed something that reshaped our whole picture of existence. The more distant a galaxy was, the faster the galaxy was rushing away. Not in one direction, but in every direction at once, as though the entire universe was swelling. That simple relation, distance tied to speed, is now called Hubble's law, and the relation is the first firm evidence that the cosmos is expanding. The picture people often reach for is a loaf of raisin bread rising in a warm oven. As the dough swells, every raisin drifts away from every other raisin, and from the point of view of any single raisin, all the others appear to be fleeing, with the farthest raisins fleeing fastest, simply because more swelling dough lies between them. No raisin sits at the centre, no raisin is being pushed, the bread itself is growing, and the raisins ride the growth. Galaxies are the raisins, and the space between the galaxies is the rising dough. We are not at the centre of the expansion, because the expansion has no centre. Every observer on every world in every galaxy sees the same outward rush, and could be forgiven for thinking themselves the still point of it all. So when astronomers want the distance to a faraway galaxy, they can spread the light of the galaxy into a spectrum, measure how far the colours have been shifted toward the red, and read off how fast the galaxy is receding, which by Hubble's law tells them roughly how far away the galaxy must be. This smooth outward flow, the steady swelling of space that carries every distant galaxy away, is what astronomers call the Hubble flow. And laid gently on top of that smooth flow is the smaller private drift we met earlier, the peculiar motion, each galaxy leaning toward whatever is dense and away from whatever is empty. Subtract the smooth swelling, and what remains is the fingerprint of gravity, the very thing the great flow maps are built to read. Redshift, in the end, is how we measure the size of the universe and the speed of the growing, one stretched colour at a time. Now pull back farther still, leave the basin, leave Shapley behind, draw away until even 500 million light-years stops being a useful ruler. Draw away until the universe no longer resembles a sky of galaxies and begins to look like something else entirely. And at that scale, the strangest fact about the cosmos finally comes into view. The galaxies are not sprinkled about at random. The galaxies lie along threads. They lie along threads of varying thickness, varying density, varying length, and the threads join one another at heavy luminous knots, the way the veins of a leaf meet at their junctions, the way nerves run through corridors of tissue in a body. The knots are where the great clusters of galaxies settle. The threads are where the smaller galaxies and groups string between one cluster and the next, and the gulfs between the threads are vast, dark, and very nearly empty. The whole pattern, at the largest scale we have ever mapped, looks less like a sky and more like the inside of a living thing. We call the pattern the cosmic web. The web is the largest organised structure that exists. Where did such a thing come from? The answer reaches all the way back to the first moments after the birth of the universe, and the answer rests on the invisible material we met earlier around the Milky Way. In the beginning, the young cosmos was very nearly smooth, a hot fog of matter and light spread almost perfectly evenly in every direction. But not quite perfectly. Woven through that fog were faint ripples, regions very slightly denser than their surroundings, differences no greater than about 1 part in 100,000. Those ripples were the seeds. Gravity is patient and relentless, and gravity always favours the crowd. Wherever matter was a touch denser, that region pulled in a little more, which made the region denser still, which let the region pull harder yet. Over billions of years, the faint ripples deepened into a network. Dark matter, unable to shine but able to fall, gathered first, draining out of the emptying regions and pooling along ridges and knots, building an invisible skeleton. And ordinary matter, the gas that would one day become stars and planets and people, followed the dark matter down, streaming along the skeleton, light in the framework from within. The cosmic web is what a nearly smooth beginning becomes after gravity has worked on the beginning for 13 billion years. We know the story is right partly because we can build the story inside a machine and watch the same web appear. Feed a supercomputer the physics we trust, the gravity and the dark matter, and those faint initial ripples measured in the ancient background glow. Press play and let the simulated universe run. Great efforts of this kind carry names like the Millennium Simulation and, more recently, Illustrious TNG, projects that follow millions upon millions of parcels of matter as gravity draws the parcels together across simulated eons. And what emerges every single time, without anyone placing the pattern there by hand, is a frothy, threaded, tangled web of filaments and knots and hollow voids that look startlingly like the real universe our telescopes reveal. That agreement is one of the quiet triumphs of modern science. We can take the faint whisper of ripples from the dawn of time, hand the whisper to gravity inside a machine, and watch gravity build the same cathedral of threads that we see hanging in the actual sky. For a long time, though, those simulations and the statistics drawn from galaxy counts were the only cosmic web we had. Neither one was a picture in the ordinary sense. Both were very well-founded guesses. Neither was a photograph. It is worth saying a little more about what those simulations actually taught us, because the simulations did more than reproduce a pretty pattern. When astronomers first built universes inside machines, they could try alternatives. They could run a cosmos made only of ordinary matter, without any dark matter at all, and watch what emerged. What emerged was wrong. Structure grew too slowly, and the resulting universe looked nothing like the sky we actually see. Because ordinary matter, coupled to light in the hot early universe, could not begin gathering into clumps until quite late. Add dark matter, which ignores light entirely, and so can begin falling together much earlier, and the simulated cosmos suddenly matches reality. The dark matter builds the scaffolding first, in the fog, long before ordinary matter is free to move, and the ordinary gas then falls into a framework already prepared. The web we see is a fossil of that head start. Without the invisible substance, there would not have been enough time since the beginning to build anything like the structure hanging in our sky. The simulations also reveal the shape of the growth, which astronomers call hierarchical assembly, and the shape runs opposite to what most people expect. Small things formed first. Little clumps of dark matter gathered early, then merged into larger clumps, which merged into larger ones still, building upward across billions of years. Galaxies were not born full-sized. Galaxies were assembled out of smaller pieces, and the great clusters at the nodes of the web were assembled out of galaxies, and the assembly is still going on tonight in the crowded parts of the cosmos. The universe builds from the bottom up patiently by accumulation, and the cosmic web is simply the largest thing that process has managed to make so far. And there is a lovely honesty in how these simulated universes are checked. Astronomers do not simply look at the pictures and nod. They measure the simulated cosmos with exactly the same statistical tools they use on real galaxy surveys, counting how often galaxies fall a given distance apart, measuring the sizes of the voids, tallying the density of the filaments, and then compare those numbers against the real sky. When the numbers agree across many independent measures and many different scales, the agreement is not a coincidence of appearance. The agreement means that gravity, dark matter, and a set of faint ripples from the dawn of time really are enough to explain the largest structure in existence. That is a remarkable thing to be able to say about a universe. Then, in January of the year 2025, the situation changed. A team using a very patient instrument on a very large telescope at the European Southern Observatory in Chile reported the first direct image in high definition of a single strand of the cosmic web. Led by a doctoral researcher named Davide Tonotti, working with colleagues at the Max Planck Institute for Astrophysics, the group had spent hundreds of hours season after season, staring at one carefully chosen patch of sky between two distant young galaxies in the early universe. Their instrument, called Muse, gathers not just an image but a full spread of colours for every single point in view, which let the team pick out the faint, particular glow of intergalactic hydrogen and lift that whisper of light clear of the surrounding darkness. And what the team finally saw, faint as breath on cold glass, was the cosmic web made visible, a glowing tendril of gas about 3 million light-years long, threading from one young galaxy to the other, its light having travelled just under 12 billion years to reach the telescope. Real, photographed, present. The web is not only a model, the web is a thing. When the team laid their photograph beside the matching strand pulled from a supercomputer simulation, the two looked like siblings. The guess and the glass agreed. And that one strand now lives in the record. The team is already hunting for more. If that photograph showed us a single thread in exquisite close-up, the year 2026 brought the opposite gift, the wide view, the map. Using the James Webb Space Telescope, a survey called Cosmos Web charted the positions of more than 160,000 galaxies across a deep, narrow core sample of the universe, reaching back through most of cosmic history, and placed each of those galaxies within the larger scaffolding of the web. Where the strand from Chile was a single fibre seen up close, the Webb survey was the cartography, the atlas, showing where the great structure runs across enormous reaches of space and time. Put the two together, and you have something new in the history of our species. From one direction, a space telescope draws the full sprawling skeleton of the cosmos. From the other, a ground-based instrument resolves for the first time what a single bone of that skeleton actually looks like from up close. The largest structure in existence, approached at last from both ends at once. When you let these pictures settle, something quietly extraordinary steps into the light. Astronomers enjoy running a certain calculation, and the answer is one of the most lopsided numbers in all of physics. Most of the volume of the universe, very nearly all of the volume, is empty space inside the voids between the filaments. The threads themselves take up only a thin sliver of the cosmic volume. By one careful estimate, the cosmic web, the entire connected high-density network of filaments and nodes, holds about 35% of all the mass in the universe, packed into less than 1% of the volume. Most of the mass lives in the threads. Most of the volume lives in the gaps. The universe is, in this very precise sense, mostly a sculpture of emptiness, with all the matter that exists strung along narrow lines of higher density that run through the dark. And the threads themselves, very slowly, are doing something no one quite predicted. In late 2025, another team reported that they had measured the motions of galaxies along one particular cosmic filament, a stretch some 50 million light-years long running between two clusters, and had found that the galaxies were not simply sitting there. The galaxies were turning. The whole filament was rotating slowly around its own long axis, and the galaxies inside were spinning in step with that turning. We do not fully understand the reason. On the simplest theories, the cosmic web should have no need to rotate at all. The most promising idea is that as matter fell onto each thread from either side, the sheets of infalling gas and galaxies met at an angle rather than head-on, and the shear between them set the whole filament gently spinning, the way two currents meeting in a river can raise a slow, turning eddy. Whatever the cause, the motion unfolds on a scale so immense that one full turn of one such filament would take many times the present age of the universe to finish. The threads are not still. The threads are slowly, patiently turning. That slow turning has a smaller echo, and the echo runs all the way down to the individual galaxies. When astronomers began looking at how galaxies are oriented relative to the filament each galaxy sits in, they found the orientations were not random. Galaxies tend to be aligned with the thread they belong to, their spins and their shapes bearing a relationship to the direction of the filament running through their neighbourhood. Larger galaxies, particularly the great ellipticals near the knots, often have their long axes lying along the filament, pointing down the thread. Many smaller spiral galaxies show a tendency to spin with their axes arranged in a preferred way relative to the filament as well, though the details vary, and this is an area where astronomers are still working things out carefully. The reason, as best we understand, reaches back to how each galaxy was assembled. A galaxy does not gather gas from all directions equally. A galaxy gathers gas mostly from along the filament feeding it, the material arriving down the thread rather than raining in evenly from every side. That directional feeding hands the growing galaxy a preferred axis, a memory of the geometry of the larger structure, written into the way the galaxy turns. Which leads to a thought I rather love. When you look at a photograph of a spiral galaxy, at the direction of the spin and the tilt of the disk, you are not only looking at an isolated object, you are looking at a record of the shape of the cosmic web in that galaxy's neighbourhood billions of years ago, preserved in the rotation of 100 billion stars. The largest structure in the universe has left its fingerprints on the smallest details of the objects the structure contains. Let us pause for a moment at one of the great knots where the threads of the web cross, because the knots reward a closer look, and the knots hold a secret that will matter later tonight. A knot at full size is a cluster of galaxies, hundreds or even thousands of galaxies bound together by gravity into a single swarm. From a distance, the swarm looks like a scattering of bright islands. But the space between these islands is not empty. The space between the galaxies in a cluster is flooded with gas, and the gas is astonishingly hot, heated by the sheer depth of the cluster's gravity to tens or even hundreds of millions of degrees, so hot that the gas shines not in visible light but in X-rays. Astronomers call this the intracluster medium, and here is the detail that surprises almost everyone who first meets the fact. In a typical great cluster, that thin hot gas between the galaxies weighs more than all the stars in all the galaxies of the cluster combined. The galaxies are the bright ornaments. The gas is most of the ordinary matter, glowing faintly in a register our eyes cannot see. That hot gas does something dramatic to any galaxy unlucky enough to plunge through the cluster at speed. As a galaxy dives inward, the dense intracluster gas presses against the galaxy's own gas like a headwind, and the pressure strips the galaxy's gas away, tearing a long streaming tail out behind the galaxy as the galaxy falls. Astronomers call the process ram pressure stripping, and the galaxies caught in the act are so striking, trailing their bright tails of gas and newborn stars, that astronomers have nicknamed them jellyfish galaxies. One famous example drifts inside the very Norma cluster we just visited, unspooling a glowing tail behind itself as the cluster's hot gas peels the galaxy bare. So the knots of the cosmic web are not quiet places. They are the great crowded cities of the universe, filled with a searing invisible atmosphere heavier than all the stars, wherein falling galaxies are slowly stripped of the gas they need to make new stars. Hold that hot cluster gas in mind, because when we reach the deep spaces between the threads, we will meet a thinner, stranger cousin of the same fire. So we have galaxies, clusters, superclusters, basins, threads, nodes, and walls. And the walls deserve a quiet chapter of their own, because the walls are where the story begins to press against the very foundations of what we believe about the universe. Here and there across the cosmic web, the filaments refuse to stay thin. In places they thicken into broad sheets and tangled reaches that astronomers call great walls. Long draped regions of higher than average density, sometimes 1 billion light years across or more. The Sloan Great Wall is one. Astronomers found the Sloan Wall in the year 2003, buried in the data of a great sky survey, a region of slightly denser cosmic web stretching across roughly 1.5 billion light-years of space. The CFA Great Wall, found back in the late 1980s by the astronomers Margaret Geller and John Huchra, was the first such structure ever recognized. A few 100 million light-years long, a soft, bright stripe laid across the maps of the day. When Geller and Huchra first plotted their slice of the sky and saw that stripe emerge, the pattern was so unexpected that the discovery helped launch the entire modern effort to map the large-scale universe. Each wall holds many thousands of galaxies, threaded across distances no signal anyone ever sends will live long enough to cross. It is worth pausing to marvel at how we came to see the cosmic web in the first place, because the seeing did not come easily. A telescope pointed at the sky gives you a flat picture. The galaxies scattered across that picture might be near or far, and nothing about their appearance on the flat sky tells you which. To turn that flat scatter into a true map, you need the third dimension, the depth, and depth is exactly what redshift provides. Measure how far the light of each galaxy has been stretched toward the red, and Hubble's law hands you the distance. Do this for one galaxy, and you have a single point in space. Do this for thousands, and a shape begins to emerge from the dark. In the 1980s, a team led by the astronomers Margaret Geller and John Huchra set out to do exactly that, patiently measuring the redshifts of galaxies in a narrow slice of sky, one galaxy at a time, and plotting each on a map of real three-dimensional space. What emerged from that first slice startled everyone who saw the map. The galaxies did not fill space evenly, the way anyone might have assumed. Instead, the galaxies traced out great arcs and chains, wrapped around enormous empty bubbles, with vast dark voids where almost no galaxies lay at all. In one famous version of the map, the pattern of galaxies happened to resemble a little standing human figure, and astronomers fondly nicknamed the shape the Stick Man. Nobody had put that structure there on purpose. The froth of walls and bubbles and voids had simply appeared the moment the flat sky was given depth. For the first time, human beings were looking at the cosmic web directly, drawn out of raw starlight by the patient counting of redshifts. From that first slender slice, the surveys grew and grew. Later efforts mapped tens of thousands, then hundreds of thousands, then millions of galaxies, sweeping across ever larger volumes of the sky, and every new survey confirmed and deepened the same astonishing pattern, the same lacework of filaments and knots and hollow voids reaching as far as the telescopes could see. The cosmic web was not a quirk of one small slice. The cosmic web was the architecture of everything, and each new map simply drew the same great structure in finer and finer detail. The Sloan Wall deserves a moment more, because the wall gives a sense of what these structures actually contain. Threaded through that vast draped region are hundreds of individual galaxy clusters and groups, each one a knot of the kind we visited earlier, each with its own crowd of galaxies and its own searing atmosphere of intracluster gas. Not far from the older CFA wall sits the Coma cluster, one of the richest nearby clusters known, holding well over 1,000 galaxies in a single gravitationally bound swarm. Coma is the very cluster where Fritz Zwicky first noticed that the galaxies were moving too fast for the visible matter to hold, which means the first evidence for dark matter came from studying one bright knot of the very web that dark matter had built. The scaffolding was discovered by looking at what the scaffolding was holding up, and the walls have a shape worth picturing properly. A great wall is not a solid barrier and not a flat plate. A wall is a broad, irregular sheet, where several filaments have run together and thickened, more like a wide region of denser weave in a loose fabric than like anything built. If you could travel through one, you would notice nothing resembling a boundary. You would simply find galaxies appearing a little more frequently for a very long stretch of your journey. The crowd thickening gently and then thinning again over hundreds of millions of light years, with no wall of any kind ever coming into view. The names we use are honest about the pattern and misleading about the substance. There's nothing to run into out there. There's only the slow gathering and slow scattering of galaxies, drawn across scales too large for any word in our language to hold comfortably. Beyond the walls, astronomers began to notice even larger hints, groupings so wide that the very word structure started to strain. Using quasars, the brilliant beacons of light thrown out by feeding black holes in the young universe, a team charted what they named a huge, large quasar group, a loose association of dozens of quasars sprawling across something like 4 billion light years. Each of these discoveries pushed a quiet, nagging question further into the open, and that question sits at the heart of everything we will meet for the rest of this chapter. How large is the universe allowed to let a single structure grow? The question is not idle, because our entire standard picture of the cosmos rests on an assumption called the cosmological principle. The principle says that on large enough scales, the universe should look essentially the same everywhere and in every direction. Smooth, even, no special places, no vast lumps, no enormous patterns. Zoom out far enough, the principle promises, and every region should resemble every other, the way a sandy beach looks uniform from a distance even though the beach is made of countless individual grains. Cosmologists can even estimate the scale at which this smoothing ought to take hold, the distance beyond which lumps should average away into blandness. That scale is often placed at around 1 billion light years, or a little more. Any structure much larger than that should not really exist. The universe should not be able to organize matter into a single coherent thing wider than roughly 1 billion light years, because there simply has not been enough time since the beginning for gravity to assemble anything grander. So when astronomers began finding candidate structures several times larger than that limit, a genuine unease crept into the field. Either the structures are not truly single connected things, and we are being fooled by chance alignments, or the cosmological principle, one of the deepest assumptions in all of cosmology, has a crack running through the middle. Two of the strangest of these candidate structures were found by the same person, a researcher named Alexia Lopez, working through her doctoral studies at the University of Central Lancashire. Her method is a thing of quiet cleverness. When the light of a distant quasar passes through intervening gas on the long journey to Earth, certain atoms in that gas absorb particular colours, stamping thin dark lines into the quasar's spectrum. By treating thousands of distant quasars as backlights and reading the absorption stamped into each one, Lopez could map where cool gas, and therefore galaxies and clusters, lay strewn across enormous depths of space. And in that map, twice she found something that should not have been there. The first, announced in the year 2021, she called the Giant Arc, a vast, gently curving sweep of galaxies and gas stretching across roughly 3.3 billion light-years, lying some 9 billion light-years away, so that the light defining the arc set out when the universe was little more than half its present age. 3.3 billion light-years is nearly 3 times the supposed size limit for any single structure. Then, a few years later, in the same broad region of sky, and at very nearly the same distance, Lopez found the second. She called the second the Big Ring, an almost perfect ring of galaxies and clusters about 1.3 billion light-years across, with a circumference of nearly 4 billion light-years. If the Big Ring could somehow be seen with the naked eye, the ring would span an area of sky as wide as 15 full moons laid side by side, and the two structures, the arc and the ring, sit as cosmic neighbours, seen at the same distance, at the same era of cosmic time, only about 12 degrees apart in the sky. From current theory, we would expect at most a single structure of such scale in the entire observable universe, and Lopez had found 2 of them sitting side by side. In her own careful words, neither structure is easy to explain within our present understanding, and their sizes, their shapes, and their nearness to one another must surely be telling us something important, though what exactly, no one can yet say. Now, honesty demands that we hold this the way careful astronomers hold it, and there is real debate. Not everyone agrees that the Giant Arc and the Big Ring are genuine, single, connected objects. Some researchers have argued that patterns of this apparent scale can arise by pure chance, even in a perfectly ordinary universe, that our eyes and our pattern-seeking minds can knit true randomness into shapes that feel deliberate, the way we find faces in clouds. One study made exactly that case, suggesting that gigantic apparent patterns can appear in standard simulations without meaning anything. Lopez and her colleagues answer that challenge in turn, arguing that the earlier work had shortcomings, and that once those were corrected, patterns like the arc and the ring were not casually reproduced by chance after all. So, the matter stands unresolved tonight, a genuine open question at the frontier. Either these ultra-large structures are real, and one of the foundations of cosmology needs mending, or they are a subtle trick of statistics, and the principle holds. What is not in doubt is that the question itself is real, and that thoughtful people are still arguing it out with the data in front of them. That is not a weakness in the science. That argument is the science, caught in the middle of doing its slow work. And then comes the largest claim of them all, the structure that pushes this entire question to its breaking point, and one that must be handled with the greatest care of all. Back in the year 2013, a small team of astronomers led by Istvan Horvath, Jon Hakila, and Zsolt Bagoli were mapping the positions of gamma-ray bursts. A gamma-ray burst is the most violent kind of explosion the universe knows how to make, a flash of light released in the death throes of certain massive stars or the collision of dead ones, so brilliant that a single burst can briefly outshine everything else in the sky at those wavelengths and be seen clear across the observable universe. Because the bursts are so bright and so distant, they make excellent markers for where matter gathered in the young cosmos. And as the team plotted the bursts, they noticed an oddity. In one particular direction, very far off, around the constellations of Hercules and Corona Borealis, the bursts were clustered far more thickly than chance should allow. If the bursts were tracing the structure of the early cosmic web, that concentration might mean a filament, not a small filament, an enormous one. They named the possible structure the Hercules Corona Borealis Great Wall, and here is a small human detail I find rather wonderful. The rather grand name was not coined by a professor at all, but suggested by a Filipino teenager, an aspiring astronomer named Jondrick Valdez, and the name simply stuck. The scale of the thing, if real, defies comparison. The early estimates put the length of the Hercules Corona Borealis Great Wall at around 10 billion light-years, which is already more than a tenth of the entire observable universe held in a single thread. And in the year 2025, the same core team returned with more data and a fresh analysis, and rather than shrinking under scrutiny, the wall grew. The new work suggested the structure might extend even farther than before, by some measures reaching toward 15 billion light-years, and might sit somewhat closer to us than earlier thought, because certain nearer bursts turned out to belong to the pattern too. 15 billion light-years. There are no comfortable words for a number like that. The structure would be so large that light itself, crossing at the only speed there is, could not travel from one end to the other in anything close to the current age of the universe. Set against the roughly billion light-year limit that the cosmological principle allows, a wall of that size is not a small exception. A wall of that size is a problem. So does the Hercules Corona Borealis Great Wall break the rules of cosmology? The honest answer is that we do not yet know, and the people closest to the work are the first to say so. Gamma-ray bursts are rare, and mapping a structure from their scattered positions is a delicate statistical art, vulnerable to the same trap that shadows the giant arc and the big ring. A cluster of bursts in one patch of sky might trace a genuine connected superstructure, or might be a chance crowding that only looks like a wall. Many astronomers remain unconvinced that the wall is one continuous object rather than a statistical fluke, and settling the matter will take far more data than we currently hold. A proposed future space mission, sometimes called Theseus, is designed in part to gather gamma-ray bursts by the thousands with precise distances, which is exactly the kind of catalogue needed to finally confirm the wall or dissolve the wall back into noise. Until then, hold the Hercules Corona Borealis Great Wall the way you would hold any beautiful object whose true nature you cannot yet name. The wall might be the single largest thing that exists. The wall might be a shape our minds have drawn across scattered points of light. Both possibilities are in their own way astonishing, and the coming years of patient survey work will slowly tell us which of the two we are living inside. All of this raises a question you may have been quietly carrying, and the question has a genuinely strange answer. How much of the universe can we actually see? Is the cosmic web we've been mapping the whole of the thing, or a small window onto something much larger? The honest answer is that we see a bubble, and the bubble has a definite edge, though the edge is not a wall. We can only see out to the distance that light has had time to cross since the beginning. Look far enough in any direction and you eventually reach light that set out at the very dawn of things, the ancient background glow we met earlier, and beyond that boundary there is nothing to see, not because nothing is there, but because the light from farther out has not yet arrived. Astronomers call this bubble the observable universe, and here is the first surprise. The universe is about 13.8 billion years old, so you might reasonably expect the bubble to be 13.8 billion light-years in radius. Instead, the radius is more like 46 billion light-years. The reason is expansion. While the light was travelling toward us, the space the light had already crossed kept stretching, carrying the source ever farther away. So the most distant matter we can see, whose light left when the universe was young, now sits some 46 billion light-years off, giving the observable universe a diameter of something like 93 billion light-years. Inside that bubble, our best estimates place the number of galaxies somewhere in the range of hundreds of billions, perhaps considerably more when the faintest and smallest are counted. Every one of those galaxies sits somewhere in the cosmic web, on a filament or in a knot or drifting lonely in a void, and the web itself, as far as we can tell, does not stop at the edge of our bubble. The pattern simply continues out past the limit of our sight, filaments and voids and clusters carrying on in every direction, into regions whose light will not reach us for billions of years, and in some cases will never reach us at all. What lies beyond the edge of the observable universe is not a different kind of place. What lies beyond is almost certainly more of the same, more threads, more hollows, more slow rivers of galaxies, drifting through a darkness we will never be told about. So the maps we have drawn tonight, magnificent as they are maps of a window. The cosmic web is not 93 billion light-years across. The cosmic web is at least that large, and quite possibly very much larger. And the portion of the structure we happen to be able to see is set not by the size of the structure, but by the age of the light and the patience of the universe. Now drop back gently from these unimaginable lengths and let us turn to what actually fills the spaces in between. So far we have talked about how the galaxies arrange themselves, and how the threads carry them along, and how the walls press against the limits of what the universe should allow. We have not yet talked about the space between the threads, the voids, the deep cosmic emptiness, and what waits there when we look with care turns out to be stranger still than the architecture above it. For almost all of human history, whenever our ancestors thought of space at all, they assumed the space was simply nothing, a perfect blank, the plain absence of matter. Even as modern science took shape, the old idea lingered that the regions between the stars and between the galaxies were essentially pure vacuum. The truth, once we finally measured it, turned out to be far more subtle. Yes, intergalactic space is almost empty, in any human sense of the word, empty. But the word almost is doing very strange work in that sentence, and to feel how strange, we need to walk the emptiness down step by step. Picture a small room, a bedroom, say. The room runs about 3 meters in each direction, floor to ceiling, wall to wall. Filled with ordinary air, that room holds roughly 10 trillion molecules, a number so large that reading the number aloud would take longer than the room has stood. Step off the Earth, and a room-sized pocket of space in low orbit holds only a few hundred molecules. Already we have fallen from 10 trillion to a few hundred, and we have barely left home. Travel out of the solar system into interstellar space, among the stars of our own galaxy, and the number falls again, to something like 80,000 particles in that same room. 80,000 sounds like a crowd until you remember what 80,000 is replacing, and interstellar space, thin as the space is, remains far richer than what lies ahead. Now leave the galaxy behind, drift out into intergalactic space, the gulfs between the great threads of the cosmic web, and the count drops further still, by an amount that genuinely strains the imagination. In a typical region of intergalactic space near a filament, the average density of ordinary matter runs to something like 1 atom for every 10 cubic meters. 1 atom, in a volume the size of a small bedroom. And in the deep voids, in the true hollows between the filaments, the number falls further yet, to perhaps 1 atom for every 100 cubic meters, or fewer. 1 atom in a volume the size of a small house. These are not poetic guesses. These are measurements, taken by watching how light bends and dims as the light crosses those regions on its long journey to us from distant quasars. The voids are real. The emptiness is real. The emptiness has been measured, and the voids are not small. Earlier tonight I promised we would return to a famous emptiness, the one you may have met in other space videos, and now we have arrived. Out toward the constellation of Bootes lies one of the great hollows of the nearby universe, a roughly spherical region of profound emptiness so wide that light needs something like 330 million years to cross from one side to the other. Astronomers found the Bootes void back in the early 1980s, and the discovery unsettled people, because a hole that large did not fit the tidy picture of a smoothly sprinkled universe. Inside a region where the ordinary density of galaxies would predict thousands of bright members, only a few dozen faint galaxies drift, scattered like a handful of lonely lamps across a country the size of a continent. One astronomer put the loneliness memorably. If the Milky Way had formed in the heart of the Bootes void, we might not have known that other galaxies existed at all until the middle of the 20th century, because there would have been almost nothing near enough to see. Sit with that quietly. Whole galaxies do exist inside the great voids, but they exist in a kind of profound isolation, each one adrift in a darkness so wide that its nearest neighbours are almost beyond reach. Let us stay inside the great emptiness a little longer, because the voids are not simply blank, and what lives in them tells us something about how galaxies grow. Even the deepest hollows contain a few galaxies scattered thinly, and astronomers call these void galaxies. They are, as a group, curiously different from the galaxies that live along the crowded filaments. Void galaxies tend to be smaller, bluer, and richer in gas, often still busily forming new stars long after their crowded cousins have settled into quiet middle age. The reason seems to be simply that nothing has ever happened to them. Out along the filaments and inside the great clusters, galaxies are constantly harassed. They collide, they merge, they plunge through the hot gas of clusters and have their own gas stripped away. They are stirred and heated by their neighbours. In the voids, none of that ever happens. A void galaxy drifts in a solitude so deep that nothing has ever come close enough to disturb the galaxy, and so the galaxy keeps its gas and keeps making stars gently, for billions of years longer than the galaxies in the busy parts of town. There's a thought experiment here that I find quietly haunting, and I offer it gently. Imagine a world orbiting a star inside such a galaxy, deep inside one of the great voids. The sky over that world would look, at first, much like our own, full of the stars of its own galaxy. But when the astronomers of that world built their first telescopes and turned them outward, they would find almost nothing. where we see thousands of galaxies scattered across every patch of dark sky, a telescope in the deep void might find a handful, faint and impossibly far. The evidence that the universe is filled with other islands of stars, the evidence that took our own astronomers only a century to gather, might take them very much longer, or might arrive so faintly that the truth stayed in doubt for generations. They would be living inside the same cosmic web as us, subject to the same physics, made of the same atoms, and yet the sky would tell them a far lonelier story than ours tells. And this is worth remembering when we speak of the voids as empty. They are not empty of everything, they are empty of company. The material is there, thinly, and a few galaxies drift within, and the great hollows are as much a part of the architecture as the threads. What the voids lack is neighbours, and in a universe where almost everything interesting happens when things meet, that lack is the whole of the difference. Here is a thought that may unsettle you a little, and I offer the thought gently, because the thought is genuinely debated and far from settled. We have spoken all night of the voids as the empty places between the threads, as though we ourselves lived comfortably on a bright filament looking out at the hollows. But there is growing evidence that our own patch of the universe is emptier than average. Some astronomers, studying how the density of galaxies falls off around us out to great distances, have argued that the Milky Way sits inside a very large, gently underdense region, a soft hollow sometimes called the local hole, spanning perhaps 1 billion light-years or more, within which galaxies are thinner on the ground than the cosmic average. If that is right, and the point remains contested, then we're not perched on a thread admiring the voids from outside. We are living partway down inside one of the shallower hollows ourselves, in a slightly rarefied corner of creation, and this possibility has teeth, because a local underdensity would subtly change how fast the nearby universe appears to be flying apart. There is a stubborn disagreement in cosmology, often called the Hubble tension, between two different measurements of the universe's expansion rate that ought to agree and do not. A large local hollow could, some argue, ease part of that disagreement, because galaxies inside an underdense region are drawn outward toward the denser walls around the region, adding a little extra apparent speed to the local expansion. Whether the local hole is real, and whether the hollow truly helps with the Hubble tension, is still being argued out. But the mere possibility is humbling. The empty places we've been visiting all night may not be somewhere else. One of them may be here. There is one more void worth visiting before we turn back to the threads, and this one hides not in the sky of galaxies, but in the ancient light itself. When astronomers first mapped the faint background glow left over from the birth of the universe, that nearly uniform hiss of microwaves reaching us from every direction, they found the glow astonishingly smooth, mottled only by the tiny warm and cool ripples we met earlier. But in one particular patch of sky, toward the southern constellation of Eridanus, they found something odd, a region noticeably colder and larger than the ripples alone should ever produce. Astronomers named the region the cold spot, and the origin of the cold spot has been argued over ever since. One elegant idea points to a giant hole in the nearby universe. If an enormous void, emptier than average, happened to lie between us and that patch of ancient light, the void could chill the light passing through by a subtle effect tied to the expansion of space. Light falling into a void has to climb back out again on the way to us, and in a universe whose expansion is accelerating, The void grows shallower during the crossing, so the light climbs out of a slightly weaker well than the well the light fell into, and loses a little energy in the bargain, arriving cooler. And in exactly that direction, astronomers did find a supervoid, the Eridanus supervoid, a vast under-dense region spanning something like 1.5 to 2 billion light-years and running about 20% emptier than the cosmic average. Careful mapping, using the gravitational bending of light from a great galaxy survey, confirmed that the supervoid is genuinely there and is in fact the most prominent large underdensity in the whole surveyed region. But honesty asks me to leave the door open, because the case is not closed. When astronomers work out how much the Eridanus supervoid should chill the ancient light under our standard model of the universe, the void accounts for only perhaps 10 to 20% of the cold spot's depth, not the whole of it. The supervoid is real, but the supervoid may not be the full answer. Some researchers think the cold spot is simply a rare but ordinary fluctuation in the primordial glow present from the very beginning. Others have floated stranger ideas still, so the cold spot remains a genuine open puzzle, one of those loose threads at the edge of cosmology that no one has yet managed to tie off. A cold patch in the oldest light there is, sitting quietly in the sky, still waiting for its full explanation. But here comes the gentle paradox at the heart of the emptiness, the thing that makes the voids and the thin gas along the filaments stranger than a simple vacuum. That astonishingly sparse material between the galaxies is not cold. The material is hot. Along the filaments, where matter grows just slightly denser than in the deepest hollows, the few atoms that exist sit at temperatures of hundreds of thousands of degrees, and sometimes millions. This material has a name. We call the material the warm-hot intergalactic medium, which physicists usually shorten, almost fondly, to WIM. The WIM is so thin that detection is nearly impossible. The WIM burns so hot that the gas gives off no visible glow at all, shining instead only in faint low-energy X-rays. And until quite recently, the WIM was the answer to one of cosmology's most embarrassing mysteries. The mystery ran like this. Cosmological theory, built on what we know of the universe's first few minutes and on the ancient background glow left over from the beginning, predicted with real confidence how much ordinary matter should exist. Not the mysterious dark matter, but the plain familiar stuff, the protons and neutrons that make up stars and planets and breath and bone. The theory named a specific quantity. Then astronomers went out and counted. They tallied the stars, the glowing gas inside galaxies, the dust, the great clouds of hydrogen strung between the stars, everything ordinary matter they could find and measure. And the total came to only about half of what the theory demanded. Half of the ordinary matter in the universe was simply missing. Not the exotic dark matter, which is a separate puzzle entirely, but half of the ordinary, countable, everyday atoms that the universe was supposed to contain. The missing half had to be somewhere. The numbers of physics do not lie about totals like this. But the missing half sat nowhere our telescopes had yet managed to look. To find the missing half, astronomers had to learn to see the invisible gas that fills the space between galaxies, and the trick they developed is one of the most elegant in all of astronomy. The gas itself is far too thin and too faint to glow in any way we can easily catch, but the gas lies in the path of light coming from beyond. so astronomers use the brightest distant beacons in the universe, the quasars, those blazing cores of young galaxies where matter spirals into a giant black hole and releases tremendous light. A quasar shines across billions of light years, and on the long journey to us, the quasar's light passes through cloud after cloud of intervening gas. Each cloud drinks a particular sliver of colour out of the beam, leaving a thin dark notch in the rainbow of the quasar's light. Spread that light into a spectrum and you find not one notch but a whole dense thicket of them, a picket fence of absorption lines, each line the shadow of a separate cloud of hydrogen strung along the line of sight at a different distance. Astronomers call that thicket the Lyman Alpha Forest, and reading the forest is like reading the growth rings of the intervening universe. Every dark line is a cloud we could never see directly, betrayed only by the shadow the cloud casts on a light from beyond. Through the forest, the invisible skeleton of gas between the galaxies slowly becomes readable. Since we have leaned so heavily on quasars tonight, using them as backlights to read the invisible gas, the quasars themselves deserve a moment, because they are among the most violent objects the universe has ever produced, and they sit at the very hearts of the web's brightest knots. A quasar is what happens when a supermassive black hole, of the kind we met at the centre of the Great Elliptical in Virgo, is not resting quietly but feeding. Gas spirals inward toward the black hole, crowding and grinding against itself as the material falls, heating through friction and compression until the infalling matter glows with a ferocity that beggars description. A single quasar can outshine the entire galaxy surrounding the quasar, hundreds of billions of stars together, from a region of space not much larger than our own solar system. Some fire enormous jets of charged particles out of their poles, beams that punch clear out of the host galaxy and reach for hundreds of thousands of light years into the space beyond. For our purposes tonight, the quasars matter for two reasons, and both are lovely. First, quasars are beacons. Because a quasar shines so brilliantly, a quasar can be seen from almost unimaginable distances, which makes each one a lamp held up behind the intervening universe. Every thin cloud of hydrogen strung along the sightline stamps a dark absorption line into the quasar's light, and by reading that forest of shadows we map gas we could never see directly. Practically everything we know about the thin material between the galaxies in the early universe we learned by reading the shadows cast on quasar light. The most violent objects in existence turn out to be our gentlest surveying tool. Second, the quasars tell us when the great knots of the web were assembling. Quasars are overwhelmingly creatures of the early universe, look far away, and therefore far back in time, and quasars are common. Look nearby, in the present era, and quasars have largely fallen silent. Their black holes still there, but no longer feeding at anything like the old rate. That shift is a record of the web's own history. In the young universe, gas poured down the filaments in abundance. Galaxies collided frequently at the crowded nodes, and matter was driven inward to the black holes in torrents, lighting them up. As the gas thinned and the collisions grew rarer, the feeding slowed and the beacons dimmed. The quasars are the flare of the web's assembly, still visible tonight only because their light has taken so long to arrive. Using exactly this kind of shadow reading, the first solid capture of the missing matter arrived in the year 2018, when a team led by an Italian astronomer named Fabrizio Nicastro reported that they had found the missing baryons in absorption against the X-ray light of a distant quasar. The missing matter, the team showed, lay exactly where the simulations had long placed it, spread out between the galaxies, held in the HIM, strung along long, faint filaments, too hot to glow brightly, too thin to absorb light in the ordinary way, hiding in plain sight where no one could easily see. Not in any mystical fashion, not through any wonder of the gaps, simply because what a telescope can detect depends entirely on what that telescope was built to detect. The whim had always been present, filling the spaces between the galaxies with thin, hot, ionized matter, threading along the same filamentary lines as everything else. We could not see the whim because our eyes and our older instruments were tuned to other registers of reality. Once we built the right kind of X-ray telescope and looked through the telescope at the right kind of background light, part of the missing half of the universe's ordinary matter very quietly came home. But the Nicastro result was only the first thread of the answer, a single sight line, a beginning. The full confirmation, the one that finally weighed the hidden gas across the whole sky, came only very recently, and the confirmation arrived from one of the strangest messengers in modern astronomy. In the year 2025, a team led by the astronomer Liam Connor turned to fast radio bursts. A fast radio burst is a flash of radio energy from some distant galaxy, lasting only 1,000th of a second, yet releasing in that instant as much energy as the sun pours out across days. What makes these flashes so useful is what happens to each one on the journey to us. As a burst crosses the thin ionized gas between galaxies, the different frequencies of the flash are slowed by slightly different amounts, so that the pulse arrives smeared out in time, stretched like a cord whose notes reach the ear a heartbeat apart, and the amount of that smearing measures with beautiful directness exactly how much matter the flash passed through on the way. Every ionized particle along the entire path leaves its mark on the timing. Connor and his colleagues gathered 60 of these bursts, ranging from one only about 12 million light-years away in a nearby galaxy, out to the most distant fast radio burst ever recorded, a flash from some 9 billion light-years off. By measuring how much each burst had been smeared, the team could finally take a proper census of the ordinary matter strung between the galaxies. And the answer settled the mystery. More than 3/4 of the universe's ordinary matter, they found, drifts in the thin gas between the galaxies, in the cosmic web and the medium threaded through the cosmic web, precisely where the theory had insisted the missing matter must be. The old embarrassment was over. The baryons were never truly lost. The baryons were simply spread so thin and hidden so well that we needed radio flashes from across the universe to find the home address of the matter. As one of the astronomers put it, the decades-old question was never whether the matter existed. The question was always where. And now we know. 3/4 of the ordinary universe floats between the galaxies in the almost empty places we have spent tonight learning to see. And here is the strangest thing of all about that hidden gas, the here, now that we know where the missing matter has been hiding. In human terms, the gas runs extraordinarily hot. Hot enough that any solid object set inside would in principle be heated. Hot enough that each of the few atoms present carries enormous energy. And yet, if you could somehow stand within the whim, you would feel no heat whatsoever. You would feel nothing at all, because temperature is one thing and warmth is quite another. Temperature measures how fast the individual particles are moving. Warmth measures how many of those particles actually reach you and hand over their heat. In the WIM, the particles are racing at millions of degrees, but so few particles exist that the average time between one of them striking your skin is measured in seconds or longer. Your body would not warm. Your body would in fact grow steadily colder, shedding its own heat into a near vacuum that gave almost nothing back. You would freeze inside a region of space technically hotter than the surface of the sun, because the universe's largest reservoir of ordinary matter is so sparse that the temperature of the gas has no grip on anything at all. I want to rest on that a moment, because I find the fact strangely beautiful. The greatest physical store of ordinary matter in the universe is not in the stars, and not in the planets, and not in any of the things we usually picture when we imagine cosmic stuff. That store is in the warm, hot intergalactic medium, drifting along the threads of the cosmic web, present nearly everywhere, touched almost nowhere. A vast, quiet ocean of thinly stretched hydrogen and helium at temperatures we associate with violence and yet so still and so dilute that nothing meaningful can be done to the gas by anything that exists. The WIM is hot, and the WIM is empty, and the WIM is most of the ordinary stuff there is. So this begins to be the shape of the whole picture, once you pull back far enough to take everything in at once. The universe looks like a great dark sculpture made mostly of nothing. A few percent of the volume is claimed by the cosmic web, where the filaments and the walls and the clusters carry the galaxies in long luminous strings. And across the great gulfs between those threads, in the voids that fill most of the actual volume of existence, drifts the thin hot ocean of stretched matter, glowing faintly in X-rays, cradling most of the rest of the universe's ordinary atoms. Almost everything that is lies in the threads. Almost everything that is not lies in the spaces between, and the universe, taken whole, is far, far more space than substance. But I've been speaking all night of an invisible scaffolding, of dark matter draining out of the voids and pooling along the ridges to build the framework, and I owe you an honest account of why anyone believes in a substance no telescope has ever seen. Because the claim sounds, at first hearing, like a story told to patch a hole. The reason astronomers hold to the claim, and hold to it firmly, is that the evidence arrived from many different directions at once, and every direction pointed the same way. The first hint came back in the 1930s, from a sharp and prickly astronomer named Fritz Zwicky, studying a great swarm of galaxies called the Coma Cluster. Zwicky measured how fast the galaxies in that swarm were moving, and found them racing about so quickly that the visible matter, all the stars in all those galaxies, came nowhere near enough gravity to hold the swarm together. By every account, the cluster should have flung itself apart long ago. Something unseen, something far more massive than everything that shone, had to be holding the swarm in place. Zwicky called the missing substance dark matter, and for decades the idea sat quietly at the edge of the field, too strange for most people to embrace. The idea moved to the centre in the 1960s and 1970s, largely through the patient work of the astronomer Vera Rubin, who studied not swarms of galaxies but the insides of single spiral galaxies, measuring how fast the stars orbited at different distances from the centre. By the ordinary rules, stars far out at the edge, where the visible matter thins to almost nothing, should orbit slowly, the way the outer planets crawl around our sun. Instead, Rubin found the outer stars racing along just as fast as the inner ones, galaxy after galaxy, as though each spiral were embedded in a vast hidden halo of unseen mass reaching far beyond the glowing disk. The stars were telling her in their motion that most of every galaxy is invisible. This is the same dark halo we met around the Milky Way at the very start of the night, and Rubin's work is a large part of why we are so sure the halo is there. The cleanest proof of all came much later, from a distant wreck called the Bullet Cluster, where two great clusters of galaxies had smashed through one another. In that collision, the ordinary gas of the two clusters, which makes up most of the visible ordinary matter, dragged and slowed and piled up in the middle, glowing in X-rays where the crash was fiercest. But the gravity of the two clusters, mapped by a method I will describe in a moment, did not stay with the gas. The gravity sailed on ahead, clean through the wreck, carried by two invisible clumps that had passed through the collision almost untouched. The mass and the visible matter had come apart. The gravity was somewhere the glowing stuff was not. There is no comfortable way to explain that separation, except that most of the mass in each cluster was dark matter, which barely interacts with anything, and so slipped straight through the crash, while the ordinary gas snarled up in the middle. And the method that mapped the gravity in that wreck is the very tool that lets us weigh and chart the invisible web directly, so the method deserves a proper introduction. When light from a distant galaxy passes a large mass on the way to us, the mass bends the path of the light, the way a lens bends a beam, because gravity curves the space that light travels through. A great concentration of matter, even invisible matter, will gently distort and smear the shapes of the more distant galaxies seen behind the concentration, stretching their images into faint arcs and slivers. By measuring how the shapes of millions of far galaxies are subtly stretched, astronomers can reconstruct the map of all the mass lying in front of them, seen and unseen alike. This is called gravitational lensing, and in its most delicate form, weak lensing. The effect on any single galaxy is far too small to notice, revealing the hidden mass only when the faint distortions of countless galaxies are averaged together. With weak lensing, we no longer have to infer the dark scaffolding only from motion. We can photograph the gravity itself. And when astronomers do this across wide fields of sky, the mass maps that emerge show exactly the filaments and knots and voids of the cosmic web, drawn now not in starlight but in pure gravity, the invisible skeleton made faintly visible at last by the bending of ancient light around the skeleton. There is one more ghostly ingredient woven through everything we have seen tonight, and the ingredient is worth a gentle mention, because the ingredient helped shape the very texture of the web. Alongside the ordinary matter and the dark matter, the universe is filled with an almost unimaginable number of neutrinos, feather-light particles born in vast quantities in the first moments after the beginning. Neutrinos barely interact with anything at all. Trillions upon trillions of them are streaming through your body this very second, through the Earth, through the Sun, as though the solid world were not there. And because neutrinos are so light and move so close to the speed of light, the neutrinos resist being gathered. Where dark matter falls readily into the ridges and knots of the web, the swift neutrinos tend to stream straight out of the smaller clumps before gravity can hold them, gently smoothing away the finest details of the structure, like a warm breath softening the sharpest edges of a frost. This gives astronomers a subtle and beautiful tool. The exact texture of the cosmic web, how sharp or how smooth the smallest structures are, depends in part on how much the neutrinos weigh, a number physicists have struggled for decades to pin down in the laboratory. So by mapping the fine grain of the web across enormous volumes of the universe, astronomers can effectively weigh the neutrino from the cosmos itself, reading the mass of the lightest known particle in the softness of the largest known structure, and the mapping is not finished. In fact, the mapping has barely begun, and the next 20 years may reshape everything we have discussed tonight. Right now, a great instrument in the mountains of Arizona is gathering the spectra of millions upon millions of galaxies and quasars, building the largest three-dimensional map of the universe ever attempted, and the map is what has begun to hint that dark energy may be changing over time. A European space telescope is surveying an enormous fraction of the sky from beyond the Earth, measuring the subtle distortions in the shapes of billions of distant galaxies in order to chart the invisible dark matter scaffolding directly through the bending of light. And on a mountaintop in Chile, a new observatory with an enormous camera has begun repeatedly photographing the entire southern sky, night after night, building a record of the change in heavens with a completeness nobody has ever had before. Put those efforts together and the coming decade should give us the cosmic web in a detail that would have seemed like fantasy a generation ago. The great unresolved questions we have handled carefully tonight, the reality of the largest walls, whether Laniakea drains into a greater basin, whether dark energy is truly steady or slowly weakening, whether the cosmological principle survives contact with structures like the Big Ring, are not permanent mysteries. They are questions with data already coming in. Some of them may well be settled within the lifetimes of most of us listening. I find that a quietly hopeful thing to end a survey on. We're not looking at a finished map. We're looking at the earliest, roughest sketch of the largest object anyone has ever tried to draw, made by a species that has only had proper telescopes for 4 centuries and has only known other galaxies exist for about 100 years. 100 years ago, the accepted view was that the Milky Way was probably the whole universe. In a single human lifetime, we went from that to mapping a web of filaments spanning billions of light years, to photographing a single thread of the web directly, to weighing the invisible matter between the galaxies using radio flashes from the far side of the cosmos. Whatever the next 100 years bring, we are extraordinarily early in this, and the view is already magnificent. The very small and the very large, once again, turn out to be quietly telling the same story. We have talked about the faint ripples in the early universe as the seeds of everything, and we can do better than talk about them, because we have their photograph. When the universe was very young, barely a few 100,000 years old, the whole of space was a glowing fog, hot and dense and opaque, so crowded with free particles that light could not travel in a straight line without being scattered almost at once. Then, as the universe expanded and cooled, a threshold was crossed. The particles joined into neutral atoms, the fog cleared, and for the first time light could stream freely across space. That first liberated light is still travelling now, stretched and cooled by billions of years of expansion into a faint hiss of microwaves, reaching us from every direction at once. We call the light the cosmic microwave background, and the light is, quite literally, a photograph of the universe as the universe looked at the moment the fog cleared, the oldest light there is. And that photograph is not perfectly smooth. When astronomers measured the ancient glow with exquisite care, they found the light very slightly warmer in some directions and very slightly cooler in others, by only a few parts in 100,000, a faint mottling across the whole sky. Those tiny warm and cool patches are the seeds themselves, the primordial ripples caught at the very instant before gravity began the long work of deepening them. The warmer, denser patches are the places where matter was already gathering just a little more thickly. Trace those patches forward across 13 billion years of patient gravity, and the slightly denser regions grow into the filaments and the knots and the clusters, while the slightly emptier regions drain and widen into the voids. The cosmic web we have travelled through tonight is simply what those faint patches in the baby picture become when gravity is given enough time. We can look at the seed and the flower in the same night, the ripple in the ancient light and the great sculpture the ripple became, and know that the one grew into the other. There is a further secret written into those ripples, and the secret has become one of the most powerful rulers in all of cosmology. In the hot early fog before the light broke free, the denser patches did not simply sit still and grow, they rang. Pressure and gravity fought one another in the crowded plasma, and the struggle sent sound waves rolling outward through the fog, spheres of compression expanding from every dense seed like the sound from a struck bell. When the fog cleared and the pressure vanished, those expanding waves froze in place, leaving each original seed ringed by a shell of slightly enhanced density at a very particular radius, a preferred distance stamped into the matter of the universe. Astronomers call this frozen ringing the baryon acoustic oscillations, and the preferred distance stretched by expansion comes to about 490 million light-years in today's universe. That distance shows up ever so faintly as a favoured spacing between galaxies across the whole cosmic web, a gentle preference for pairs of galaxies to sit that far apart, an echo of a sound that rang out when the universe was young. And because we know the true size of that frozen ring, we can use the ring as a standard ruler laid across the sky, comparing how large the ring appears at different distances to measure how fast the universe has expanded across cosmic history. The largest map ever made of the universe, built by the Dark Energy Spectroscopic Instrument from the positions of millions upon millions of galaxies and quasars, is in large part a hunt for this frozen ringing, reading the ancient bell across billions of years to trace the expansion of everything. The web is not only a sculpture, the web is a recording of the first sound. Before we leave the threads behind and turn to the fate of all this architecture, I want to give the filaments one last, more intimate look, because the threads are not only the scaffolding of the universe, the threads are how galaxies are fed. Remember the glowing strand from Chile, the first filament ever directly photographed, threading gas between two young galaxies in the early universe. That image was not only a portrait of structure, that image was a picture of nourishment in progress. For a galaxy to keep making stars, the galaxy needs a steady supply of fresh, cool gas, and left to itself, a galaxy would exhaust the local supply and fall dark. What keeps the great galaxies alight across billions of years is the gas flowing down the filaments toward the galaxy. Cool streams following the invisible scaffolding inward, delivered along the threads of the web to the hungry centres where stars are born. Astronomers sometimes call these cold flows, rivers of gas running down the cosmic web into the galaxies at the nodes. Around each galaxy, the incoming gas gathers into a vast turbulent envelope, the circumgalactic medium, a churning reservoir far larger than the visible galaxy itself, where gas arriving from the web mixes with gas thrown back out by exploding stars, and from which fresh star-making material rains down onto the galaxy. So the filaments we mapped as the skeleton of the universe are, at the same time, the feeding tubes of the galaxies. The same threads that hold the cosmos in shape carry the raw material of stars and planets, and eventually of us, down out of the intergalactic dark and into the bright places where matter comes alive. When the team in Chile traced the boundary between the gas belonging to the galaxies and the gas belonging to the web, they were watching, in a single faint image, the exact place where the universe hands its raw material over to the making of new worlds. So let us stand back now and watch the whole story unfold in time, from the smooth beginning to this present moment, because the cosmic web has a history, and we are living in one particular chapter of that history. In the beginning, after the fog cleared, the universe fell dark. There were no stars yet, only the faint cooling glow of the background light and vast clouds of hydrogen and helium settling gently along the first shallow ridges of the dark matter scaffolding. Astronomers call this long quiet stretch the cosmic dark ages, and the dark ages lasted for many millions of years, a universe of gathering shadow with nothing yet alight. Then, along the densest threads, where the gas had pooled most thickly, the first stars finally ignited, blazing to life in the deep dark, and the cosmic dawn began. Those first stars were fierce and short-lived, and their light and their deaths began to reshape the gas around them. Galaxies assembled at the nodes where the threads crossed, drawing in gas along the filaments, growing and merging and lighting up the framework of the web. Star formation across the universe climbed to a great peak, a cosmic noon, when the young galaxies blazed with new stars far more furiously than galaxies do today. And then, slowly, the fires began to bank. The gas supply along the filaments thinned, star formation gradually eased from its early fury, and the universe settled into the calmer, more mature phase we live in now. The great web fully drawn, the galaxies strung in place, the whole structure turning slowly through a long afternoon. When you look out at the cosmic web tonight, you're looking at a structure that took the entire age of the universe to build, glimpsed in the quiet middle of the structure's life. That first ignition deserves a closer look, because the moment when the darkness ended was also the moment the web became visible for the very first time. Those earlier stars were not like the stars we know. Forged out of gas containing nothing but hydrogen and helium, with none of the heavier elements that later generations would use to shed heat and fragment into smaller pieces, the first stars grew enormous, some perhaps hundreds of times the mass of our sun. They burned ferociously and briefly, blazing with fierce ultraviolet light, and they died young in tremendous explosions that scattered the first heavier elements out into the surrounding gas. Every atom of carbon in you, every atom of oxygen in the air you're breathing, every atom of iron in your blood traces back through a long chain of stellar generations to those first furnaces lighting up along the ridges of the young cosmic web. Their light did something else, something that reshaped the whole universe. The ultraviolet flood from the first stars and the first feeding black holes tore electrons off the neutral hydrogen that filled all of space, converting the calm, neutral fog back into a thin, charged, transparent plasma. Astronomers call this the epoch of reionization, and the process spread outward from each bright source like bubbles of clarity growing in a dark fog, expanding, meeting, merging, until the bubbles joined and the fog was gone. The universe became transparent for the second time and has remained so ever since. When you look out tonight at the light of distant galaxies crossing billions of light years without being absorbed, you are looking through space that was cleared by the very first generation of stars, working outward from the same filaments and knots we've been tracing all evening. There is one more consequence worth holding, because the consequence explains something we met earlier. That reionization is why the gas between the galaxies today is ionized rather than neutral, its electrons stripped away and running free. And ionized gas is exactly what a fast radio burst passes through on the journey to us, and exactly what smears each burst out in time and lets astronomers weigh the hidden matter. The census that finally found the missing ordinary matter of the universe was only possible because the first stars, more than 13 billion years ago, stripped the electrons from the intergalactic dark. The oldest fires in the universe left the medium in the precise state that let us, in this decade, finally count the universe's atoms. But the middle of a life is not the end, and the picture I have drawn for you, true as the picture is not still. The cosmic web is not a finished sculpture. The threads, the voids, the basins, the walls, none of them stand fixed. The universe is very slowly doing something to its own architecture, and the direction is consistent, and no known force runs the process backward. The space between the threads is very gradually growing larger, not because anything is pulling the threads apart, not because anything is pushing, but because the universe as a whole is expanding, and the expansion is not slowing. For most of cosmic history, we believed the expansion ought to be easing, gravity gradually applying the brakes to whatever the beginning had set in motion. We were wrong. About 5 or 6 billion years ago, very roughly, the expansion began instead to accelerate. Something woven into the fabric of space itself, which physicists have named dark energy, almost as a placeholder for our own deep ignorance, is causing more and more new distance to open between things, faster and faster as time runs on. The threads of the cosmic web are not breaking. The threads are simply being held together by gravity, while everything around them lengthens and empties. The story of how we learned about that acceleration is worth telling, because the discovery was an accident, and the people who made the discovery did not believe their own result at first. In the 1990s, 2 rival teams of astronomers set out to measure how quickly the expansion of the universe was slowing down. Everyone assumed slowing was the answer. Gravity pulls, matter attracts, and a universe full of galaxies ought to be gradually applying the brakes to its own expansion. The only real question was whether the braking was strong enough to one day halt the expansion altogether and pull everything back together, or whether the universe would coast outward forever, slowing but never stopping. To measure the braking, both teams used a particular kind of exploding star. Certain white dwarf stars, the dense cinders left when a sun-like star dies, can be pushed past a critical limit by material drawn from a companion, at which point the dwarf detonates in a titanic explosion. Because the detonation happens at very nearly the same critical mass every time, these explosions all shine with very nearly the same true brightness. That makes each one a standard candle. Measure how bright such an explosion appears from Earth, compare the appearance with the known true brightness, and you can work out how far away the explosion happened. Measure the redshift as well, and you learn how much the universe has expanded since the light set out. Gather enough of them at enough distances, and the expansion history of the cosmos falls out of the data. When the results came in the year 1998, the distant explosions were fainter than they should have been. fainter means farther. Farther means the universe had expanded more than anyone expected during the light's long journey. Both teams, working separately and checking each other with some suspicion, reached the same impossible conclusion. The expansion was not slowing at all. The expansion was speeding up. The astronomers involved have spoken since about how thoroughly they distrusted the result, hunting for errors in the dust corrections, in the calibrations, in the assumptions, because the finding overturned an expectation almost everyone in the field had carried for a lifetime. The errors were not there. The result held, and the discovery went on to win the Nobel Prize in Physics. That single unexpected faintness in a scattering of exploding stars is the entire observational foundation of dark energy, the thing now thought to make up most of the energy content of the universe, and the thing that will, across enormous spans of time, gently take the cosmic web apart. We did not predict dark energy. We did not want dark energy. We went looking for the brakes and found the accelerator instead. Now here honesty asks me to open a door onto a live and unsettled question, one of the most closely watched puzzles in cosmology right now, so hold this part lightly. For a long time we assumed that dark energy was perfectly steady, a fixed property of space, the same strength everywhere and for all time. That assumption has a name, the cosmological constant, and the assumption has served us well. But the great galaxy maps I mentioned earlier, the ones hunting the frozen ringing of the early universe, have begun to hint at something stranger. As of the most recent results, gathered by that international survey from millions of galaxies and quasars, there are growing signs, not yet certain, that dark energy may not be constant at all. The data hint that the strength of dark energy may have been slightly greater in the past and may be gently weakening as the universe ages. Taken alone, the measurements still sit close to the old steady picture, but combined with other lines of evidence, the hints have grown difficult to dismiss, and some of the researchers involved have begun to say, cautiously, that our standard model of the universe may need revising. I want to be clear that this is not settled. This is the frontier, the place where the data are still coming in and thoughtful people still disagree. But if the hints hold, then the very thing driving the great emptying of the cosmic web may itself be changing over time, and the far future of everything may be harder to predict than we thought. Since we've touched on the expansion twice tonight, let me lay out one more honest disagreement, because the disagreement is currently among the sharpest in all of cosmology, and nobody has resolved it. The question is simply how fast the universe is expanding right now, and there are two good ways to find the answer, and the two ways do not agree. The first way looks back to the beginning. Take the faint ripples in the ancient background glow, add the frozen ringing of those early sound waves that we met in the great galaxy maps, feed the measurements into our best model of how the universe evolves, and the model tells you what today's expansion rate should be. The measurements involved are exquisitely precise, and the answer comes out at a particular value. The second way ignores the beginning entirely and simply measures the nearby universe directly. Start with stars whose true brightness we can establish by careful, ladder-like steps, work outward to exploding stars in more distant galaxies, and read the expansion straight off the sky, here and now. This method has also become extremely precise, and the answer comes out noticeably higher than the first method, by something like 8 or 9%. 8% does not sound like a crisis until you appreciate how small the uncertainties on both measurements have become. Astronomers have spent years hunting for a mistake, checking calibrations, re-examining assumptions, bringing in new instruments and independent techniques, and the gap has stubbornly refused to close. The disagreement now carries a name, the Hubble tension, and the tension has become one of the central puzzles of the field. Either there is a subtle error hiding in one of these very careful measurements, or the universe is doing something our standard model does not capture. Some new ingredient or some change in the behavior of dark energy over cosmic time. Notice how this connects to everything else we've handled carefully tonight. A large local underdensity might contribute. A dark energy that weakens with time might contribute. The unresolved questions in cosmology are not scattered independent puzzles. They have a habit of pointing all together toward the same few gaps in our understanding, which is usually a sign that something genuinely new is waiting to be found. There is one more consequence of the great emptying, and this one is not far in the future at all. This one has already happened, and it happened without a sound. Because the expansion of the universe is accelerating, there is a boundary out beyond which our influence can never reach. Not a boundary of sight, but a boundary of contact. Send a signal today at the speed of light in any direction you like, and that signal will reach every galaxy within a certain range, and no galaxy beyond it, no matter how long you wait. Because the space between us and those farther galaxies is opening faster than the signal can close the gap. Astronomers call that limit the cosmic event horizon, and the horizon lies somewhere around 18 billion light-years away, in the stretched distances cosmologists use. Everything within is, in principle, reachable, given enough patience. Everything beyond is permanently mathematically out of contact, and here is the number that stops me every time. Almost everything we can see already lies beyond that line. Of all the galaxies visible in our sky tonight, the overwhelming majority, something like 94% of them, are already unreachable. Their light is still arriving, ancient and faithful, so we can see them perfectly well. But nothing we ever send will arrive. No message, no probe, no signal, not in 1 billion years, not in 100 billion. The window during which contact was possible closed long before anyone was here to notice. We are looking at a sky full of places we can observe in detail and can never touch. A gallery of images whose originals have already passed out of reach. More than that, the line is still moving. As the expansion continues to accelerate, galaxies that are currently just inside the horizon drift steadily out across the boundary, quietly and without incident, at a rate of many thousands of stars every second. Nothing dramatic happens when a galaxy crosses. No flash, no sound, no change in the view. The galaxy simply becomes, from that moment, a place we could never have reached even in principle, though the light already on its way continues to arrive for a very long time afterward. Right now, as you lie there, the reachable universe is very slowly shrinking, and the visible universe is not, and the gap between those two numbers is the strangest and quietest fact in cosmology. I've often wondered whether that thought should be sad, and I do not think it is quite. There is a version of this that reads as loss, a universe of doors closing one after another, but there is another version, and I like the second one better. Every one of those unreachable galaxies is still sending us its light. The light was sent long ago, from places already beyond our grasp, and the light is still coming, still crossing the widening dark, still arriving at the mirrors of our telescopes tonight. Nothing about the distance stops the message. The universe has arranged things so that we cannot go, but we can always look, and the looking is generous beyond any reasonable expectation. Almost every part of the great structure is visible to us. Almost none of it is available to us. And the whole of astronomy, in a way, is the art of being content with that arrangement. There is a question that tends to surface when anyone spends long enough looking at the cosmic web, and the question is not really about structure at all. If the observable universe holds hundreds of billions of galaxies, and each galaxy holds hundreds of billions of stars, and a great many of those stars carry planets, then the number of worlds strung along the threads of the web is beyond any counting we can meaningfully do. Somewhere in that vastness it is difficult to believe that nothing else ever woke up and looked at the sky. And yet the sky is silent. We have been listening in a serious way for decades now, and nothing has ever called back. That silence is a famous puzzle, and I will not pretend tonight to solve a thing that has resisted much cleverer minds than mine. But the architecture we've been mapping does put the silence in a particular light, and the light is worth sitting with. Whatever else may be out there, the cosmic web has arranged matter in such a way that the distances between the bright places are almost perfectly designed to prevent contact. Even within our own galaxy, a conversation across a few thousand light-years would take longer than our species has practiced agriculture. Question and answer separated by an interval no civilization is guaranteed to survive. Between galaxies, the situation is not difficult but closed. A message to the nearest large galaxy would take 2.5 million years to arrive, and the same again for any reply. And by then everything about both parties would have changed beyond recognition. So it may be that the universe is full of company, and that the emptiness we have traced tonight is the reason we have never heard from anyone. Not because the void is hostile, and not because we are alone, but because the web binds everything gravitationally while separating everything conversationally. Each luminous knot keeps its own counsel. Each thread carries matter beautifully and messages hardly at all. That is not a tragedy exactly, though the thought has a certain weight to it in the quiet of the evening. It is simply the shape of the place, a structure of unimaginable connection, made of unimaginable distance, in which every bright island can see nearly all the others and speak to almost none of them. What that future holds, if we follow the current picture forward, is gentle and a little sad. The dense regions of the cosmic web, the clusters and the deeply bound basins, are held together by their own inward gravity. Our local group is held together. The Virgo cluster is held together. The dense core of the Shapley supercluster is held together. These structures will endure. Expansion will not tear them apart, but the filaments and the strands strung between them, the long, thin connections, are not bound tightly enough to resist. Across enormous spans of time, the threads will thin, the connections between clusters will stretch until the light along them fades, and each gravitationally bound region, including our own, will slowly become an island, cut off from all the others by an ever-widening gulf of dark. If dark energy instead grows stronger over time, a scenario some have called the tearing, the emptying could one day reach even inside the bound structures, unbinding clusters and galaxies and finally worlds. If dark energy weakens, the emptying may be gentler and slower than we feared. Which of these futures is ours depends on the very question the galaxy maps are only now beginning to probe. None of this, I should say clearly, will happen soon. None of this will unfold on any timescale a civilization might live to watch. The galaxies are going nowhere on human terms. Andromeda will still hang in our sky tonight, exactly where Andromeda always hangs, drifting toward us at about 110 kilometers a second, wholly indifferent to dark energy at the scale on which that galaxy is bound to us. The local group is safe. The Virgo cluster is safe. The cosmic web at the scales we actually live in is safe. But over hundreds of billions of years, across spans the universe has not yet had the time to perform, the great architecture will simplify. The web will fade. The basins will draw apart into isolation. The voids will grow. And what remains, very far in the future, will be a handful of widely separated luminous islands, each one floating alone in the dark, knowing nothing of the old neighbours except by what was long ago written in their light. If you follow that thinning out to the end, the universe has a long and remarkably orderly future ahead, and I find the shape of the future oddly soothing rather than bleak. We live now in what astronomers sometimes call the Age of Stars, the era in which the universe is full of shining things. That era is not permanent. Star formation across the cosmos has already passed its peak and is slowly declining, because the gas along the filaments is gradually being used up and locked away inside stellar remnants. Given enough time, the last clouds capable of collapsing will collapse, the last new stars will ignite, and no more will follow. After that, the universe grows patient. The brightest stars burn out quickly, but the small red ones, the most common stars of all, are miserly with their fuel and can shine steadily for trillions of years, far longer than the present age of the universe. So for an unimaginably long stretch, the galaxies will fade slowly from white to yellow to deep red, dimming by degrees, each island growing quieter and darker as the last long-lived suns run down. Then even those go out, and what remains is a cosmos of remnants, of white dwarfs cooling toward darkness, of neutron stars, of black holes, drifting in galaxies that no longer glow, separated by gulfs that have grown vaster than anything we have described tonight. And still nothing anywhere is violent about the process. There is no catastrophe in that future. Nothing explodes, nothing tears, nothing screams. The universe simply grows cooler and wider and quieter, across timescales so long that the entire history of the cosmos to this point, all 13.5 billion years of it, is barely the first breath of the story. Which means the era we're living in, the age of bright galaxies threaded on a visible web, is not the ordinary state of the universe at all. This luminous chapter is a brief early flare over almost as soon as the cosmos began, and we are living inside the flare. Every star you have ever seen belongs to the opening moments of a very long night. That thought could be melancholy. I prefer to hold the thought the other way around. Of all the eras there will ever be, we were placed in the one that shines. There is a quiet and remarkable thought buried in that far future, and the thought turns this whole night around. Imagine astronomers living on some world inside one of those isolated island galaxies, hundreds of billions of years from now. Long after the cosmic web has faded from view and the other galaxies have receded beyond the reach of any telescope, their light stretched into invisibility by the same expansion that carried them away. Those future astronomers would look out and see only their own galaxy, a single lonely island of stars adrift in what appears to be an eternal, empty, unchanging dark. With no other galaxies to observe, no receding light to measure, they would have no way to discover that the universe was expanding, no way to find the ancient background glow, no way to deduce the cosmic web or the great flowing basins or the frozen ringing of the beginning. The whole grand story we have traced tonight would be, to them, completely invisible and utterly unknowable. They would conclude, quite reasonably, that their island galaxy was the entire static universe. And here is a turn. We are not those lonely future astronomers. We are living in the brief, luminous window when the evidence is still visible, when the other galaxies still shine, when the web is still bright and the ancient light still reaches us, and the whole story can still be read. We happen to be awake at the one time in cosmic history when the universe can still be understood. That is not a small piece of luck. That is perhaps the largest piece of luck there is. So we are here in a particular kind of moment. The cosmic web is still bright. The filaments are still threaded together. The clusters are still in conversation with one another through their slow gravitational tides. The maps we have only just begun to draw are maps of a connected universe, and those maps will, very gently and very slowly, fall out of date. The connections we're tracing tonight will not be here forever. The address you carry, on a small blue world inside a small group, inside a flat sheet, on the edge of a void, inside a supercluster, inside a basin, inside a thread of the cosmic web, is a real address. And the address is also a temporary one. I find that I do not mind, not in the way I expected to. The universe has done something extraordinary, very slowly across 13.5 billion years. From a nearly uniform fog at the dawn of time, from density ripples no greater than 1 part in 100,000, gravity has raised the largest sculpture that exists. Gravity has assembled the cosmic web out of the faintest whisper of early noise. Gravity has gathered enough matter into the right places to make stars, and the stars have forged the heavier elements, and the heavier elements have made the planets, and the planets have, at least once, made you. You are part of the cosmic web. The atoms in your body are atoms that lived in the web before those atoms ever lived in you. They were drawn along the filaments, gathered at the nodes, cooked inside the stars, scattered by the deaths of those stars, recollected into our sun, laid down on your small blue planet, and finally arranged into the warm temporary form lying still in the dark and listening to a voice describe the whole arrangement. There is no separation between the great structure and the small one. We are the cosmic web, in the same way the wave is the ocean. One last thought about the threads before we let the evening go, and this one is about you. Everything we have traced tonight, the filaments and the voids and the slow rivers of galaxies, was assembled by gravity out of ripples so faint that the ripples amounted to almost nothing. 1 part in 100,000. A whisper of unevenness in an otherwise smooth beginning. If the early universe had been perfectly smooth, with no ripples at all, nothing would have ever gathered. No filaments, no knots, no galaxies, no stars, no planets, no chemistry, no anyone. A perfectly even universe would have simply expanded and cooled forever. An endless thinning fog, beautiful in a bleak sort of way, and entirely empty of events. And if the ripples had been much deeper, matter would have collapsed too eagerly, gathering into black holes early and violently, leaving a cosmos of dark, heavy things and very little light. The universe we actually got sits between those two failures, and sits there by a margin that has struck a great many physicists as remarkable. The ripples were faint enough to leave the early cosmos calm and deep enough to build everything. From that narrow setting came the whole cathedral, the web and the walls and the galaxies, and the long, slow chemistry of stars making heavier elements out of lighter ones across billions of years, until eventually some of that material found itself arranged into things that could look back out at the structure and ask how the structure came to be. I am not going to tell you what to make of that, because nobody honestly knows what to make of it, and anyone claiming certainty in either direction is going beyond the evidence. But the fact itself is worth carrying into sleep. The largest structure in existence and the small warm arrangement of atoms currently listening to this voice both trace back to the same faint unevenness in the early dark. The web made you out of the same whisper the web made itself from. You are not looking at the cosmic web from outside, you never have been. So let us come home the long way gently, and let the whole architecture pass by once more as we descend. Out at the farthest reach, the possible great walls, the vast contested threads of gamma-ray bursts and quasars, and drawn-out arcs, sprawling across billions of light-years, their reality still argued over by careful people with good instruments. Inward from those the great confirmed walls, the Sloan Wall and its companions, broad thickenings of the weave holding hundreds of clusters. Inward again, the cosmic web itself, the whole connected lacework of filaments and knots and hollow voids, most of the mass in a fraction of the volume, threaded with hot thin gas that holds most of the ordinary atoms in existence. Inward, into our own quarter of the weave, the Great Basin, the slow flow toward Shapley. Inward to Laniakea, our supercluster, 100,000 galaxies drifting toward a common floor. Inward to the Great Attractor, hidden behind the bright curtain of our own galaxy. Inward to the Virgo cluster, more than 1,000 galaxies with an enormous black hole shining at the heart of the crowd. Inward to the local sheet, our flat drifting page of galaxies, riding the edge of the local void. Inward to the local group, our small family of 80. Inward to the Milky Way, 400 billion stars turning slowly in a wheel, 100,000 light-years wide. Inward along a minor spur of that wheel, 2/3 of the way out from the centre to one ordinary yellow star. Inward past the gas giants, past the belt of rubble, to the third small rocky world. Inward through an atmosphere, through a layer of cloud, over a landscape, to a building, to a room, to a bed, to a warm and breathing creature, made of atoms that were forged inside stars and delivered here along the threads of the cosmic web, lying still in the dark, listening to a voice. The whole of the structure sits above you, holding its shape, doing what the structure has done for 13.5 billion years, and none of it needs anything from you tonight. That is enough for tonight. The threads will still be there in the morning, going about their slow work. The local void will keep gently pushing us along. Laniakea will keep falling towards Shapley. The cosmic filaments will keep turning very slowly around their own long axes in patterns we do not yet fully understand. The warm, hot intergalactic medium will keep glowing faintly in X-rays, holding most of the ordinary matter that exists out between the galaxies, where almost nothing is, doing the patient and unspectacular work of simply existing. Let your shoulders go soft, let your breathing fall slow and easy. There is nothing that needs you tonight. The universe has been holding itself gently together for 13.5 billion years, and the universe will go on doing so without the least help from anyone. You can rest now. A small warm creature, made of old starlight, on a small blue world, on the edge of a very quiet void, in the middle of an enormous sleeping architecture drifting through the dark. Good night. Sleep well.